This is section 3.5, angles of a polygon. First we need to define what a polygon is. So a polygon is a figure formed by coplanar segments called sides. They have to be in the same plane such that each segment or each side intersects exactly two other segments, one at each endpoint, and no two segments with a common endpoint are collinear. For example, each of these three shapes are polygons. They're each formed by segments, all in the same plane, segments that meet each other at each endpoint, and no two segments with a common endpoint lie on the same line. So every segment is part of a different line. Notice each of these polygons has a different number of sides. We have a basic triangle here with three sides. We have a polygon here with four sides, and then we have one here with 6 sides. Polygons can have any number of sides bigger than 3. So the triangle is the simplest polygon, and everything that we said about triangles applies to polygons. So we call the corners vertices just like we did with the triangle. Here are things that are not polygons. The first one, the one on the left, is not a polygon because it overlaps with itself. The second one is not a polygon because it has a rounded edge. The sides need to be segments. They need to be pieces of a line, and lines are straight, they're not round. And the third one is not a polygon because at the end points of each segment we don't have another segment starting. That's basically what our first condition of the definition says. Each segment intersects exactly two other segments, one at each endpoint. At each endpoint, there needs to be the start of another side. So that does not happen with this third picture on the right. Okay, those are polygons, those are not. Some polygons are called convex polygons. A convex polygon is a polygon such that no line containing a side of the polygon contains a point in the interior of the polygon. That means that if I extend the sides, those segments, into full lines, those lines will not overlap with the inside of the polygon. So this shape on the left, this four-sided thing in green on the left, is a convex polygon because if I were to extend these sides, they don't overlap with the inside of the polygon. They are all outside of the polygon. The shape on the right is not a convex polygon. We can say it's non-convex. Sometimes you'll see non-convex shapes called concave shapes. So it is a concave polygon. Because if I take this segment and I extend it into a line, that line overlaps with the inside of the polygon right here. We can't have that. We also have this segment that will overlap if I extend it into a line. If that happens with even one side, then that polygon cannot be convex. And from now on, all we're interested in are convex polygons. So if we say polygon from now on, we mean a convex polygon. And you can imagine in your mind something like this left picture, not something like the right picture. Polygons are classified by the number of sides they have. A polygon with 3 sides, we know, is called a triangle. A polygon with 4 sides is called a quadrilateral. 5 sides is called a pentagon. 6 sides is a hexagon. 8 sides is an octagon. 10 sides is a decagon. And they're actually names for any number of sides of a polygon. Those are the ones that I would expect you to know. If we have a polygon whose number of sides we don't know, or we don't want to specify because we want to talk in general about polygons, we could say it has n sides, where n is a variable representing any number, any whole number of sides, and then we would say that that is an n-gon, a polygon with n sides. When we refer to a polygon, we list its consecutive vertices in order. So if I wanted to name this polygon, I would say this it has 5 sides, so it is a pentagon. And I could call this pentagon A, B, C, D, E. Notice how I write them in order. That time I chose to go around in this direction. But I could go around the other direction. And I could also call this pentagon, and I could start wherever I want to start. Maybe I'll start with B, and maybe I'll go clockwise this time. B, A, E, D, C, and that's fine. But I want to name them in order. That way, if somebody names the polygon and I need to draw it, I'll know where to put each vertex, because I will have them in order. Okay, so we always name them in order and name them by the number of sides. This is a pentagon, and the vertices go in that order, no matter where we start. Another definition. A diagonal of a polygon is a segment that joins two non-consecutive vertices. So two vertices that are not next to each other. So I've drawn two diagonals in this red dotted line on this quadrilateral. A quadrilateral is only going to have two diagonals. If I have something with more sides, if I draw a hexagon and draw on the diagonals, there's one, there's a second one, there's a third one, there's a fourth one, there's a fifth one, there's a sixth one, there's a seventh one, there's an eighth one, and there's a ninth one. So the more sides we have, the more diagonals we have, because the more non-consecutive vertices we have that we can connect with each other. So they don't have to go straight across, as long as they are connecting any two vertices that are not next to each other. And the reason we define diagonals here is because we're going to use them right here. We know that the sum of the measures of the angles of a triangle is 180 degrees. We learned that in the last video for section 3.4. To find the sum of the measures of the angles of a polygon that could have any number of sides, let's divide up the polygon into triangles, because we know the angles of a triangle add up to 180. Let's divide our polygon into triangles by drawing diagonals, and then let's count up the number of triangles we have. If we start with a quadrilateral, and I draw in a diagonal, all I need is one diagonal in order to divide this up into triangles, and I divide it up into two triangles. So we started with 4 sides. We made 2 triangles. Okay, if I start with the pentagon, a 5-sided shape, how many diagonals do I need in order to break this up into triangles? So let's start with that one. I've got one triangle on the top there. And if I draw this diagonal, starting at the same vertex there, then I'm able to break it up into 3 triangles. And that turns out to be the smallest number of triangles that I need in order to break up my pentagon. And if I start with a hexagon, I can make one triangle really easily like that. Start with the same vertex, and I can make a second triangle there. And then 2 more triangles. I've got 1, 2, 3, 4 triangles. So I started with 6 sides, and it took me 4 triangles. That's the smallest number of triangles that I need. What do you notice about those numbers? If you take the number of sides we have, what's the relationship between that number of sides and the number of triangles that we're able to break up the pentagon in? The smallest number of triangles we're able to break up the pentagon into. They're a difference of 2, correct. If we take the number of sides and we subtract 2, that gives us the smallest number of triangles that we can break our polygon into. 4 sides, 2 triangles, 5 sides, 3 triangles, 6 sides, 4 triangles. So that leads us to understand some of the measures of the angles of the polygons, because my quadrilateral, my four-sided shape, took two triangles, so it must be 2 times 180, which is 360 degrees. And that turns out to be the sum of the measures of the angles of any quadrilateral. My pentagon, 5 sides, took 3 triangles, so it must be 3 times 180. And 3 times 180 is 360 plus 180, which is 540. And that turns out to be the sum of the measures of the angles of any pentagon, no matter what it looks like. If I measure the angles on the inside and I add them all up, it'll be 540 degrees. My hexagon, my 6-sided shape, took 4 triangles, so it must be 4 times 180. And 4 times 180 is 720 degrees. And that turns out to be the sum of the measures of the angles of any 6-sided shape, any hexagon that I take. So let's write that out in the form of a theorem. The sum of the measures of the angles of a convex polygon, any convex polygon with n sides, is n minus 2 times 180. The number of sides, subtract 2, then multiply by 180. The sum of the measures of the angles of any convex polygon with n sides is n minus 2 times 180. So if I have a 9-sided polygon, just called a nonagon, the sum of the measures of the angles of that 9-sided polygon is going to be 9 minus 2 times 180, which is 7 times 180. And what is 7 times 180? My handy dandy calculator tells me it's 1260. 1260 degrees. Any 9-sided polygon, no matter what it looks like, if I add up the 9 angles on the inside, I will get exactly 1260 degrees every time. Pretty powerful formula, and a formula you will need to memorize. One more theorem. When we've been talking about the angles of a polygon so far, we've been talking about the ones on the inside of the polygon. There are also exterior angles. We looked at those with a triangle in the last video. If we take the exterior angles of any convex polygon, this theorem says we add them all up, the sum of the measures of the exterior angles of any convex polygon, where we only take one exterior angle at each vertex. So if we have 9 vertices for a 9-sided shape, we're going to take only 9 exterior angles, one at each vertex. With a triangle, we're going to take 3 exterior angles, one at each vertex. No matter the number of sides of the polygon that I'm measuring the exterior angles of, I will always, according to this theorem, get 360 degrees every time. With a triangle, the quadrilateral, pentagon, hexagon, octagon, decagon, dodecagon, which is a 12-sided shape, doesn't matter. I'm going to get 360 degrees every time. Very different from the interior angles, which will go up depending upon a greater number of sides. This, even if I have 1,000,000 sides, still only going to be 360 degrees. Alright, one more definition and then we'll be finished. If a polygon is both equiangular and equilateral, then it's called a regular polygon. So I've drawn 4 different hexagons here. The one in the blue on the far left is neither equiangular nor equilateral. To be equilateral, all 6 sides would have to be the same length. These clearly are not the same length. To be equiangular, all 6 angles would have to be the same size. These clearly are not the same size. This one here is obtuse. This one's definitely acute. They're not all the same size. So it's neither equiangular nor equilateral. It's a very, you could say, it's the ugly hexagon. Okay, then next to it, I have an equiangular hexagon. I have all 6 angles the same size. Well, all of those angles would have to be 120 degrees because they all together have to add up to 720. I just saw that earlier. If I take 720 and divide it by 6, I get 120. So each of those angles in my equiangular hexagon are 120 degrees. But this hexagon is clearly not equilateral. This bottom side, for instance, definitely not the same size as that side. So it's just an equiangular hexagon. Next to it, though, I have an equilateral hexagon, where all 6 sides are the same length. But this hexagon is clearly not equiangular. I've got a few acute angles and several obtuse angles. Clearly not all the same size, so it can't be equiangular. It's just equilateral. On the far right, I have the perfect hexagon. In my perfect hexagon, I've got 6 equal sides, 6 equal angles. So it's both equilateral and equiangular, which makes it a regular hexagon. Those are the hexagons that I like because they're much more predictable. So notice all 6 sides are the same, and I marked those all with a 1 hash mark because they're all the same. And all 6 angles are the same. They're all, again, 120 degrees. So we like regular polygons. An example of another regular polygon that we've seen already would be a triangle. What do we call a regular triangle? Well, it's a triangle that is both all 3 sides same length and all 3 angles the same measure, so it is an equilateral and equiangular triangle. As we'll see, an equilateral triangle is always equiangular. An equiangular triangle is always equilateral. But that is not the case for higher sided polygons. That is only true for triangles. And here are your immediate practice problems. Find the sum of the measures of the interior angles and the exterior angles. So you're going to have a part A and a part B for both number 1 and number 2 of a 7-sided figure, 7-sided polygon, and a 13-sided polygon. So find the sum of the measures of the interior angles of a 7-sided polygon and the sum of the measures of the exterior angles of a 7-sided polygon. Look back at those 2 theorems we had. And find the sum of the measures of the interior angles of a 13-sided polygon and the sum of the measures of the exterior angles of a 13-sided polygon. Write all of those down at the end of your notes. And that is the end of section 3.5.